Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we're joined by Jos Van Der Westhuizen, PhD student in engineering at Cambridge University. Jos's research focuses on applying LSTMs, or long short-term memory neural networks, to biological data for various tasks. In our conversation, we discuss his paper, The Unreasonable Effectiveness of the Forget Gate, in which he explores the various gates that make up an LSTM module and the general impact of getting rid of gates on the computational intensity of training the networks. Jos eventually determines that leaving only the forget gate results in a quote-unquote unreasonably effective network, and we discuss why. He also gives us some great LSTM-related resources, including references to Jurgen Schmidhuber, whose research group invented the LSTM and who I spoke to back in TWiML Talk number 44. Before we get to the episode, I'd like to join Pegasystems, this episode's sponsor, in inviting you to meet me at the MGM Grand in Las Vegas, June 2nd through 5th at PegaWorld, the company's annual digital transformation conference. Pegasystems puts AI in the center of its customer engagement software so that it optimizes every customer touchpoint on every channel in real time. That way, each interaction is relevant and timely to each individual customer, no matter if it's a sales call, a digital marketing campaign, or a customer service chat either online or in-store. And the system is always learning in real time to make the next interaction better. Pega's customers are the real stars at PegaWorld. There you'll hear great stories of AI applied to the customer experience at real Pega customers. The event is a great way to learn from a who's who of the Fortune 500. And of course, I'll be there and speaking as well. To register, visit pegaworld.com and use the promo code TWiML19 when you sign up for $200 off. Again, that's TWiML19. It's as easy as that. Hope to see you there. And now, on to the show. All right, everyone. I am on the line with Jos Van Der Westhuizen. Jos is completing his PhD in engineering at Cambridge University. Jos, welcome to This Week in Machine Learning and AI.
Thank you, Sam.
So, we were joking earlier, you're kind of in this weird intermediate state between having finished all of the requirements for your PhD and kind of waiting to get the actual degree conferred. Tell us a little bit about your background and what you studied at Cambridge.
Yeah, so in all honesty, I fell into the machine learning field a bit by accident, and I think this story is kind of true for a lot of people with the big current hype. So where it all started is I started with biomedical engineering undergrad. I'm South African, and I studied at Stellenbosch University over there. And straight out of the undergrad, I realized that I still want to learn a bit more. So I started a master's in effectively computational neuroscience, and this is where I really had my first little experience with machine learning. We played with basic models like linear discriminant analysis and self-organizing maps. And actually, halfway through the master's, I was accepted at Cambridge and actually Oxford, and received scholarships for both. So I was quite happy, and I decided to stop the master's to go start a PhD at Cambridge. And my initial plan was to do. It was, I think, a bit ambitious, but my initial plan was I wanted to effectively create a wristwatch that could measure anything about your body, kind of look at detail at your blood, and tell you, for example, to today you have to eat a banana, otherwise tomorrow you're going to get a heart attack. That level of accuracy.
Huh. So kind of like a tricorder prize type of device.
Yeah, pretty much. And then my supervisor at the time told me oh, well, there's a range of problems that you have to solve to get to this end product. And she said one of the most fundamental ones is probably analyzing these signals and making predictions. So I kind of started, I guess, looking at ways of analyzing these signals and making predictions, and just speaking around in our really awesome lab. I heard about these temporal machine learning techniques that could easily solve this problem. And that's kind of where I started playing with them. And like I played with hidden Markov models, which is like a more conventional technique, and also with some of the new deep learning techniques like recurrent neural networks. And I guess after seeing my first few lines of like of gradient descent happening, I completely fell in love with deep learning, and that's where it all kicked off. Yeah.
Have you been seeking to apply what you've been learning about machine learning and deep learning back to these biomedical applications, or have you totally dived into the more theoretical side of ML and deep learning?
Yeah, so that's a really good question, actually. So the start of my PhD was very leaned heavily towards biological applications. And I guess my whole thesis has this whole theme as well. But pretty early on, we realized that, well, my supervisor and I realized that it's a very like tough field with a lot of red tape, and it's hard to get data. It's hard to get anything implemented. There's a lot of like bureaucracy in some areas. And I didn't like to like struggle with this during my PhD. So I think halfway through, we decided that it might be good to kind of slightly pivot towards a more theoretical kind of thesis. So it has like both aspects. But I feel strong, like I have a strong opinion that like it's the biological field, because it has all these barriers, we need to like put a lot more effort into it. So I'm quite happy that I could kind of put a lot more effort into that kind of side. Yeah.
And you mentioned that you're planning to start a company. Is it based on the work that you've done at Cambridge?
So not really. It's based on Cambridge in a way, because what I had to, because I'm from South Africa, what I had to do quite often in Cambridge is do like a Skype call back home or a WhatsApp call or all of these internet-based calls. And like after the PhD, well, I guess like even before the PhD, I knew I wanted to try and start a company. And having like, I'm sure you and a lot of other people have experienced the poor quality in any internet-based call like Skype or a WhatsApp voice call. And essentially I thought, well, why don't we just try and fix this? Like machine learning currently has achieved remarkable things in terms of generating super resolution images and like doing video interpolation. So essentially that's kind of how my colleague and I started out with the new idea that we're trying to pursue.
You're not calling it Pied Piper, are you?
I'm glad you made that connection. We're not calling it Pied Piper.
That's probably a good thing.
Yeah.
One of the papers that came out of your PhD is called The Unreasonable Effectiveness of the Forget Gate. How did that work come about?
Yeah, so maybe I'll just quickly say where the name came from. I have to give homage to Andrej Karpathy, who he had a blog post called The Unreasonable Effectiveness of RNNs, recurrent neural networks. And I think a lot of people really love this blog post, and I also love it. I read it. So that's kind of where the name inspiration came from. But to jump back to the question, essentially in the final parts of my PhD, I started working a bit like I looked at two things at the same time. One was this biological application that we had, which was to essentially infer from peripheral neural signals what an agent or what a human or some animal is doing based on those signals. And essentially, if you want to create a prosthetic device that can, like in real time, react to these neural signals, it has to be very low powered and very resource efficient. So we already had a solution that could infer what the human is doing based on those signals, but now we needed to make it much more computationally efficient. So that was like the one driver. The second, or the thing I was working on in parallel, was I looked at initialization techniques for, in general, kind of, I guess, neural networks or deep learning models, but also more specifically for LSTMs, or the long short-term memory recurrent neural network. And I guess I played around with various approaches to initialization for LSTMs, and with ways of, like, I guess, quantizing them or pruning them or making them more efficient. And then I happened to stumble upon this architecture that I've explained in the paper, which essentially did, like, first of all, we were surprised, okay, it kind of saves computation, but then, we were really surprised when it did a lot better than the original LSTM. So yeah.
Huh, interesting. Yeah, before we get too far, I should probably note, because there's somebody that's jumping up out of their chair on the BART or something like that, that the whole unreasonable effectiveness thing dates back before Karpathy to
Yeah,
a guy, Eugene Wigner, who wrote a paper, The Unreasonable Effectiveness of Mathematics and the Natural Sciences, back in 1959. But we were joking a little bit before we started the interview that I noted that I've gone through the math of RNNs several times, and it's not quite intuitive to me. And you mentioned that you have the same experience, having studied it for your degree as well. Maybe a good place to start is to talk about the or LSTMs in particular, the role of gates in LSTMs.
Yeah. So I guess I could give a little history of how it all developed. Essentially, recurrent neural networks were designed because they share parameters across this time dimension. So it makes them a lot more efficient, kind of like the same way that convolutional neural networks share parameters across the spatial dimension, the 2D spatial dimension. But one problem you run into with recurrent neural networks is that because you're kind of over time, you're multiplying the same weights or the same information with each other the whole time. You usually run into gradient problems. And back in, I think it's 97, Hochreiter and Schmidhuber realized that, or I guess they approached this from like a slightly different direction, but they thought that, or argued that you have, when you do backpropagation, you have, through a recurrent neural network, some of the, like if you want to remember something and you want to forget something of the input sequence, there's kind of conflicting updates through the same edges. So they thought or proposed that if you use an input and output gate, this could kind of solve that conflict and kind of protect. So in the RNN cell, it could kind of protect the cell or the memory from these conflicting updates. And this worked pretty well. And then I think a few years later, it was Gars in 2000 who he realized that this works well, but you can have, if the memory cell of the RNN or the like, I guess the state doesn't have a mechanism of forgetting some of the information, there's a possibility that it could grow indefinitely and kind of break down the network. So he proposed a forget gate, and this would then allow the cell to kind of forget some of the information over time. And that's kind of the LSTM that we know today. That's kind of how the gates help the LSTM to prevent these gradient problems during training.
Got it. And so the forget gate is part of the typical LSTM that is commonly in use nowadays.
Yes. So the typical LSTM has 3 gates. The input gate, which controls how much information is input at each time step. The output gate, which controls how much information is output to the next cell or to your output layer at each time step. And then the forget gate, which essentially just says, how much should I forget at each time step?
I'm trying to get at kind of your observations about the forget gate and what kind of caused you to start looking at that as an interesting part of this approach.
In 2015, there were 2 papers that kind of at the same time said or concluded that the forget gate is the most important part of the LSTM. They did like these ablation studies that removed a few gates at a time, and they kind of found that every time you remove the forget gate, like the performance just drops drastically. And this was, I think, Jos and Greff. And essentially, that was kind of my starting point. I realized, like, okay, if they say it's this important, let's remove everything we can and just keep the forget gate and see where we go from there. And it had a decent performance, but like on a typical data set called MNIST that I think everyone knows this pretty well now. If you process that in scanline order, you get many subsections that are like have 10 or 20 consecutive zeros. And essentially this makes it super hard for the network, if it's only forget gate, to remember anything by the end of those like 10 or 20 zeros. So that's where I realized, okay, we need to kind of initialize this better to be able to kind of retain memory over those periods of zeros.
I guess what's interesting about this is that it's counterintuitive. So you use the forget gate and the memory, but not the input and output gates. and found that you had this performance improvement?
Yeah. So essentially, I saw this example recently. So if you like take an image and you want to classify what's in it, essentially what like a network or what you could visualize it as is like you remove every single element of that image except the part that you care about. For instance, if it's a panda, you remove like all the buildings, branches, and like trees behind it, and you just left with the panda face or something. So essentially, like that could be summarized as to learn something, you just need to know what you need to forget. And I guess like that's kind of in a way what happens here, but it's not completely true because we have only one gate, which is the forget gate, but this gate at the moment or in the new network controls both how much information is forgotten and also how much new information comes in. So it's coupled with this gate, just like performing both of those roles.
Is that observation that learning is primarily about forgetting at odds with the emphasis on attention-based methods that seem less about forgetting and more about trying to figure out what to remember?
I think it's all just semantics in a way. It's just how you phrase it or perceive it. Yeah. So it could be either way. And I think attention mechanisms could also be said as like, oh, well, attention mechanisms just make sure that you kind of forget about the rest and focus on something that's like relevant. So it's just how you perceive it, I guess.
I'm curious, have you tried applying them in concert with one another? I'm thinking of forgetting all the way down.
All right. No, I haven't. So you mean like applying this new network with attention mechanisms?
Right.
No, I haven't tried that, but that's a pretty cool idea.
Based on this, you were inspired to create another network architecture called Janet. What is Janet about?
So Janet is essentially the network that we've been discussing now.
Okay.
So it's the Janet is just the name I gave for this new, I guess, way of processing information, or this, I guess, simplified version of the LSTM. We chose the name kind of in a lab meeting. I don't know if I'm allowed to say this, but I'll try. Essentially, I don't think that this is like a network that is the best. And because people make so many new networks every day, it's just like this is just another one of those. So it's just another network in that sense. But it happened to also be a nice little acronym for Jos's Awesome Network. So we kind of have this little lab joke about it. But yeah.
Okay, so I think what threw me off in thinking that it was a different network was the pictures that I've seen of it still have these other gates in them, or at least what look like to me these other gates. Am I reading those pictures incorrectly?
What pictures have you seen? So the gates in the Janet are essentially, it's just one gate, which is the forget gate of the LSTM. So it's like the Janet is just the LSTM with everything removed except for the forget gate.
So your paper was kind of presenting an analysis of this network and its performance on MNIST and potentially other data sets?
Mm-hmm. Yeah, so I guess we there are a few papers who that bring out new types of recurrent neural networks. This memory problem, or I guess both the memory problem over very long sequences and the problem of exploding and vanishing gradients is quite a big problem. So you have quite a few of these papers that just kind of have these benchmark memory tests. And that's kind of what we try to follow over here. So one of them is MNIST, which has this hard problem, as I mentioned before, of like consecutive zeros. Then there's perturbed MNIST, which we also tested on, which essentially just does a random permutation of all the pixels in the MNIST image. And this kind of creates longer dependencies over time if you process this in scanline order. And then there are a few others. The two we test is the add and the copy task. And essentially, it's just for the add task, it's two sequences where one is zeros and ones, and the other one is continuous values. And wherever you have ones in the binary sequence, you need to add those corresponding numbers in the continuous valued sequence. So it's like it kind of tests the memory of this network. And then the same for the copy task, just needs to remember everything at the start of the sequence all the way to the end and be able to regenerate that at the end. So yeah, and then obviously we've tested it on a few other data sets since then. For the paper, we also tested it on one of my biological data sets called MIT BIH arrhythmia dataset, which is like a data set of ECG heartbeats that are classified into 5 different types of heartbeat arrhythmias. And it worked better on that data set as well.
And when you say better relative to whatever the state of the art is on these data sets, or relative to vanilla LSTMs?
Yeah, so for the dataset, the MIT, the ECG dataset, there aren't that many, state-of-the-art results. So we just compared it to the LSTM, and it does better than the LSTM. On the other datasets, it's harder to say. So in all cases, the Janet does better than the LSTM on those datasets. But then there are like different, models that do even better than the Janet. So like the WaveNet does. I'm sure you're familiar with, the WaveNet is a new very good model by DeepMind, and that model does quite well on perturbed MNIST, but then does slightly worse than Janet on the normal MNIST. And yeah, you have quite a few of the similar nuances for other models that have also been proposed.
What was the role of the way you initialized the network in the results you saw?
For the Janet to work on datasets like MNIST, you have to initialize it using this chrono initialization scheme that we proposed in the paper. But the initialization scheme was initially proposed by Talek and Oliver. It's also a really, really cool paper in 2018, published at iClear. But if you don't use that initialization scheme for MNIST, it would, like, the Janet wouldn't learn anything. You would kind of have this accuracy around 5% throughout training. And then for tasks that are slightly easier to learn, that don't have like long consecutive periods of 0, the Janet can still learn, but it definitely does a lot better if you use this initialization scheme. For the LSTM, you also get some benefits, more stability during training if you use chrono initialization, but the benefits aren't as clear as it is for the Janet.
And how does the initialization scheme work?
Yeah, so essentially what Talek and Oliver found was that the characteristic for getting time of the RNN is of the LSTM is 1 over the forget gate value. So at the start, if we initialize it according to the way we always initialize forget gates, you essentially have a really small value for the forget gate, or a relatively small value. This means that you're forgetting the amount of time steps you can go through before you forget everything that you saw before it is limited to probably 4 or 5 time steps. And this is problematic if you need to kind of retain memory over longer periods. And they kind of said, well, okay, we can be smarter about how we initialize the forget gates. All the gates, in fact. And that is essentially to, at the start of training, the values that matter a lot for the LSTM is the biases. And initially, or traditionally, we've always just initialized them to be 0. But Talek and Oliver kind of said we should initialize them as the log of a uniform distribution between 1 and the maximum number of time steps we have. And that kind of gives you, that makes sure that some of the forget gates kind of allow the network to remember very long periods up to the end of the sequence. And some of them are still like short-term kind of cells, which kind of can't forget at every second or third step.
What's the intuition for why this specific kind of, well, first of all, did you try other initialization schemes with Janet? And if so, and there was kind of a binary, work, didn't work kind of situation, what's your intuition for why this one, performed whereas others didn't?
Yeah, so I did try a few other initialization schemes. I'm sure I've forgotten a few of them as well, because this was kind of done quite a while ago. But one of the things I tried quite a lot is, or I saw from Hochreiter and Schmidhuber, that they tried this thing in 97 as well, which they just they randomly guess some of the initial parameters between certain values. And if you do that enough, you can actually get a network that does as well as a trained one without actually ever training it. You just initialize it to this perfect network. I tried something similar where I know kind of what our current initialization schemes are, and I would kind of guess random parameters in those ranges and see kind of if this kind of yields any better networks that you can then train from or like improve from. But this unfortunately didn't work, or it gave the same results or like the same performance as you would get with a normal LSTM initialization. And then beyond that, I can't remember anything else I tried.
And how did you contextualize this within the sphere of biological applications for your thesis?
Yeah, so I think I mentioned before that we were searching for a variant of the LSTM that is computationally more efficient than just the normal one. So there are various ways you can do this. Some of them are like it's called pruning, which it comes from way back, and another one is quantization, where essentially you kind of quantize the weights to be certain values that don't take up too much memory in computation. And then I guess like I was kind of impressed by the gated recurrent unit, which is like another version of recurrent neural networks, which only use 2 gates instead of the 3 that the LSTM uses. So I was like, can we do one better than the GRU? Can we just have 1 gate and still do as well? So yeah. And then, sorry, I just remembered something from the previous question, which is in terms of initialization, one thing that I kind of found at the end was when we started using more units in the layers of the JANET and the LSTM, we found that the JANET kind of, instead of just doing better at the end, it kind of also learned a lot quicker. So it would get to the highest point of accuracy a lot quicker than it would with less units, which is kind of, yeah, that makes sense. But then I thought like a really cool thing we can try is to play around with this as in like, it's kind of, if you have a really big JANET, you can kind of just guess the right solution or very close to the right solution from the start, and then remove a lot of units to save computation, and then just train the rest to kind of give you that perfect model. So that's something in terms of initialization that I think is also worth pursuing.
Is that a potential future direction, or did you get specific results with that?
That's a potential future direction. I've been slightly busy with other things since then, but that's something I want to play with. Yeah.
Got it. What's the in general the impact of getting rid of the other gates on the computational intensity of training one of these networks?
In terms of like computational time, it doesn't improve things that much, and also I guess in just the feed forward processing time during testing. Because a lot of your like computational time is limited by the sequential nature of the LSTM, which in the case of the LSTM and the JANET are essentially the same, because you need to like process things at every time step. But the part where it does save, which also saves on, I guess, battery usage, if this is a device that's to be used in a portable device, a model to be used in a portable device, then using less memory is quite helpful. So the JANET uses half the memory that the LSTM uses and kind of gets better accuracies for the data sets that we tested on, which is quite good. And that also meant that we could train much bigger JANETs on the same GPU, whereas for an LSTM, you would quickly run out of memory on the GPU.
Did you look at the same memory and compute and power implications from an inference perspective with a trained JANET model? Is there any difference there?
No, so I'm like it's the same on that side. And so for both like training a model and for doing inference, I guess it saves half the parameters, and computational time is roughly the same. It's slightly shorter for the JANET, but nothing significant.
You noted that that compared to WaveNet, this underperforms, but is there a place for it within the domain of general purpose mobile networks, or is it, are there other reasons why it's kind of a research experiment and not necessarily practical?
It's hard to say off the bat. I think, I don't know. I was, I guess, at the time very much trapped in this very research focused, domain. I think like it's not the ultimate best solution that there is yet. I think it was kind of interesting to show that kind of this is how much importance the forget gate has in this network. It's kind of interesting to see. I think for each specific problem, you would have to have a specific like network and a specific solution that's best suited for that problem. There are some where the Janet could be that. I think specifically in like anything where you have very long-term memory requirements and only a single output at the end, and where you kind of have that requirement plus a resource efficiency requirement. I think like the WaveNet is quite a large network in terms of number of layers, but it uses very little parameters. There are pros and cons in both.
Are there specific examples that come to mind of scenarios where you'd have this long sequence in time with a single output?
So I guess like a lot of biological signals have that feature. So like if you're measuring a heartbeat for a few seconds, that's quite a lot of time steps that you have to analyze, and then you kind of have to make a single prediction at the end of all those time steps. So that's like a typical scenario where you would have a really long signal with a single output at the end. An example where it's not that like that is, for instance, when you're doing like translation, you have to generate sentence generation. You have to generate a word at each time step, or you have to classify its part of speech at each time step. That's kind of not a very long-term dependency, a long-term dependency with a single output, because you're outputting something at each time step.
Okay, cool. You mentioned in our conversation a couple of things that you'd like to play with in the future. Are there areas that you would like to see someone continue working on beyond the ones we've discussed?
No, I think I mentioned all of them. I think just applying this to more data sets, specifically data sets with long-term dependencies and a single output at the end, that's cool. So if anyone can get more types of data that are like that, I think that would be really interesting to see. And then obviously also like playing around with this new initialization feature, where you can kind of almost in the first instance guess the correct, very, very close to the correct network, and then just do a few more steps of training to get there, like a K-shot learning approach. I think those would be interesting to see.
Cool. Interesting. Well, thanks for taking the time to chat with me about this. Cool stuff.
Anytime. Thank you.
Thanks, Jos. All right, everyone, that's our show for today. For more information on Jos or any of the topics covered in this episode, visit twimlai.com/talk/240. As always, thanks so much for listening, and catch you next time.